Welcome to my video on conversion of mechanical energy. So first of all, what is mechanical energy? It's broken down into two parts. The first is going to be kinetic energy. That's going to be motion, things moving, balls, cars, rocks, it doesn't matter. Anything that moves has kinetic energy. And then it also has gravitational potential energy. And this has to do with its position relative to the Earth. And so that's what we'll call that's potential energy, and this is kinetic energy. In other words, if we have an object above the ground, it has potential energy because the gravity will pull it down. So let's write down our equation for kinetic energy. That's 1/2 mass times the velocity squared, where m is the mass of the object, and that is going to be in kilograms. That's the units. And the velocity, v, has units of meters per second. So there's our basic formula for kinetic energy. Now the potential energy, due to gravity, is going to be mgh. And let's think of that. Here's a pool down here. Here's a diver on top of a diving board. I realize I'm not a great artist, but here's our person. The person has a mass m, and they're getting ready to jump off. Now the diving board has its h. It's going to be the height of the diving board above the water. So there's our h in that equation. And g is its gravitational constant. So the potential energy, mass, just like in the other one, is going to be our mass, kilograms, the units. G is 9.81 meters per second squared. It's a unit of acceleration. That's the acceleration due to the Earth pulling on an object at the surface. And then h is going to be the height of the object above the surface of the Earth, or the two differences. You're trying to measure a difference in potential, and that's going to be in units of meters. So those are our two. We got mechanical energy broken down to kinetic, and then the gravitational, and then here's our two equations. Our equations for the kinetic energy, and then here's our equation for the potential energy. Now we know there's energy is conserved, but this is if we ignore friction and air resistance. Let's not make things too complicated for the moment. So we have conservation of energy. This is going to be an extremely important concept. It's the way nature works. So the kinetic energy initially plus the potential energy initial is equal to the kinetic energy final plus the kinetic plus the potential energy final. So the energy remains the same as long as we avoid friction and air resistance. We'll talk more about those later. So this is going to be the conservation of energy, an extremely important concept in physics. Now I'm going to do an example. Let's look at an example. We're going to do just kind of a regular straightforward example. We've got a 2 kilogram ball, and it's dropped from 15 meters up. Okay. First thing we want to know is we want to know the velocity at impact. And the second one we want to know is what's the kinetic energy at the impact. So here's our ball. It's going to be, our height here is going to be 15 meters. The mass of our ball is 2 kilograms. And we want to know the velocity just right there, right before it impacts, because it gets real complicated once it impacts the ground. So first thing we want to do, let's just use our conservation of of energy. So we know at this point up here, we're going to have, so we got the kinetic energy initially plus the kinetic energy final. Oops, that's wrong. Kinetic energy initial plus the potential energy initial is equal to the kinetic energy final plus the potential energy final. When the ball is at rest up here, it's just sitting up here before it drops, the kinetic energy is 0. So we just have potential energy. So we have mgh, that's going to be the initial when the ball is at rest up here. So their mass is 2 kilograms. Our gravitational constant is 9.18 meters per second squared. Our height is 15 meters. So now let's get our calculator out and multiply all that out. Turn it on. 2 times 9.81 times 15. Enter. Okay, so that's going to be 294.3, and the units of energy is in joules. So there's our potential energy to start with. Now we know as the ball drops just before impact, all the potential energy has been converted to kinetic energy. So the kinetic energy, you know, is 1/2 mv squared. We were given that, and that's equal to 294.3. That's going to be units of joules. So what we want to do, let's just rearrange this equation. We'll solve for v, because that's what we want to know in part A, is what is the velocity when it hits. So now, if we take the 2 over there, and the 1/2, so that's going to be 2 times 294.3. And then we can divide by the mass, which is 2 kilograms. And then that's going to be v squared. So v is going to be equal to the square root of 2 times 294.3 divided by 2, which is just the square root of 294.3. Get our calculator out again. Do our clear. There it is. So let's take the second, there it is, square root, 294.3, 17.1. So 17.15, and that's going to be meters per second. So that's our velocity. So there's our part A answer. Now, part B, we wanted to know the kinetic energy. Well, we know from the conservation of energy, that's just equal to the potential energy. So we know that that's 294.3 units of joules. So there's our two answers. We know the velocity, just at the impact, is 17.15 meters per second. And then the kinetic energy at point of impact is 294.3 joules. Well, I hope you got something out of this example and helps make you understand a little bit more about mechanical energy. And thank you for watching, and please leave a comment if you got any questions or issues. Thank you.